Thank you, thank you. Yeah, so that's a good introduction. Steals the thunder of my introduction slide, but that's all right. Today I'm going to be talking about a project I've been working on engineering a better high tunnel. So this is my About Me slide. She said most of this already, but we've got some cows, and because everybody in South Dakota needs cows, and we grow a lot of strange things. So we got hot peppers. I sell these to hot sauce makers mostly because people can only eat so many super hot peppers because they burn. But it feels a little chilly in here. I should have brought some. And passion fruit. Passion fruit are really cool. This is actually a picture of one of my previous research projects. It was a passive solar greenhouse, which will stay above freezing year-round in my location near Brookings, which is cooler than many parts of South Dakota. So it's a nice area for testing greenhouses and high tunnels. So today I'm going to talk about the High Tunnel Research Project. This is part of a research grant funded by USDA Specialty Crop Grant Block Program. And I'm going to take us through some benchmarking of traditional high tunnel performance in our area, and then talk about what are some changes that we can do to make a better high tunnel. Some of the things that I looked into is improving the frame geometry to better capture and store heat, insulating the north side so we don't lose the heat that we gain, looking at efficient roll-up vent systems, using concrete as a heat storage system that's totally passive, and then I'll take us through how this system that I put together did for its first year of performance. So first thing, I will talk about traditional high tunnel performance. This picture here happens to be one of the high tunnels we put up on the SDSU campus. And I don't have data from this yet because they just got put up this last spring, but we'll have data for this to share next year. But the benchmark system that I looked at to compare to here is one that's located within 5 miles of my location. So the weather and climate and stuff is all pretty similar. It's kind of got the standard size dimensions that you would see for a lot of high tunnels, a 34 by 96. It has a double inflated polyethylene film, and it's fan ventilated for cooling. So this side here is the exhaust vents. The far side has the fans that blow in. He's got natural gas heat, but for the data that I'll share, he wasn't using it on this one this year. It's orientated east to west, which allows it to capture the most sunlight throughout the year. And it's in a location where it gets full sun in the winter without trees or other buildings blocking it. He sets it up with tomatoes. Usually he's growing tomatoes. This here's an example picture of it from, I think it was last year in November. So he's done with production, stuff froze off, and doing the standard 8-foot tall, lower and lean tomato system. Tomatoes, usually you're planning for those tomato vines to get up to 8 feet, something to think about in your structure. For recording the temperatures and performance, I just had 3 temperature sensors located across the length of the high tunnel, and they were about 4 foot above the ground is what I usually use for measuring temperatures. If you're getting closer to the ground, it would be a bit warmer. If you go higher, it'll be cooler, and so kind of in the middle level. Some people are growing tall plants, and then you're going to care about the temperatures higher. If you're growing shorter things like lettuces and stuff, it'll be closer to the ground and warmer, but it's kind of a in the middle range. So first we'll look at what the outdoor weather did last year. So the data I'll be sharing today is from November of 2023 till October 2024, so just 1 year's worth of data. And this here is our weather data last year. The blue is what our nighttime low temperatures were, and the red is what our daytime highs, and the dotted line is the average. So if you guys remember last year, it was actually maybe unusually warm in general. So, but we did have a week or two of some nice cold temperatures where we did have a low of negative 21. That's the air temperature, not wind chill or anything. That's the actual recorded. And this is pretty typical for us. We're usually considered zone 4, 4A or B, which is a negative 25 low for the winter. So that's about right. A lot of places in South Dakota, I don't know where folks are from. It's kind of diverse, probably. If you're from West River, the temperatures will tend to be a little bit warmer than us. Our temperatures are by Brookings and Watertown. It's pretty cool because we're up on the Coteau, and so we tend to see some cool temperatures up there. But anyway, that's kind of what our overall weather looked like. So we ended up having 162 frost-free days. So our last frost was on 4/25 and got us till 10/4, which is actually about a week, maybe 2 weeks longer than I usually see. I usually see frost in September 20th or so. The first killing frost that I had for peppers, and that's shown in my picture here, was on October 1st. So the air temperature actually got down to 38, and that was cool enough for the peppers to take frost damage. And we'll talk about why. Because it doesn't freeze until 32, right? That's freezing temperatures. But when you're growing outdoors, things are a little different. So how can your plant freeze when it only gets down to 38? I'm in a little bit of a low area, so the air temperature is probably a little bit below 38. Maybe it got down to 36 that night. But heat transfer moves through several different modes. And this maybe is a little bit physics focused, but I'll talk through it a little bit because it's important for high tunnels and understanding how they perform and why they make the growing better. So heat transfer moves for plants really through two modes, through two ways. So the first way we see is convection, air convection. So cool air is moving over the plants, cools them off. That makes sense. So we get a wind, a little bit of breeze, and the plants will get cooled down to whatever the outside air temperature is. And then we also see a little bit of convection happening with the ground. So in the fall, the ground is warm, and that'll keep the plants close to the ground a little bit warmer. And so we always see frost damage, happening higher up first. But we also have radiant heat transfer happening. And this is really important because when you're outdoors, this is really what causes the plants to get colder. So what happens is thermal radiation moves the heat directly from the leaves to the cold sky. So when we want to calculate the heat transfer rate, you look at the temperature of the sky and the temperature of the plants. And the temperature of the sky will be cold. So it might be negative 40. And I've got some thermal camera pictures later on that'll kind of show that, and it's kind of cool. But you have, on a clear night without any clouds, you'll have a lot of radiant heat transfer to the sky. And so the plants can get below your ambient air temperature, and you'll see freezing. If you have a clear night, it'll get below that. If you have a cold temperature, maybe it gets down to 32 and it's cloudy, you might not freeze. Your plants might be able to survive because the radiant heat loss will be less. So now let's look at how the high tunnel performed. So I have the same weather data overlaid here, but the black line is the daily low temperature in the high tunnel, and the red line is the daily maximum that we saw in the high tunnel. And so we look at, we'll look mostly at the bottom black line here. For freezing temperatures, we had our last frost in the high tunnel. It actually is, it's not staying much above the outside air temperature in the high tunnel. It gets down pretty good at night. And so we had a total of 190 frost-free days in the high tunnel, which gave us 28 more days, and that's a big deal. At least 28 more days above 32 Fahrenheit. And there's kind of some cool things to see with the data here. In the springtime, it gets pretty cool every night, but you'll notice in the fall, the temperatures here, it's not getting down to the outside air temperature. And that's because the ground has been heated up and warmed throughout the summer, and you're getting some of that heat coming off the ground and keeping things a little bit warmer. And 28 degrees is actually, or 28 days of additional growing season is a big deal, depending on what you're growing. In the case of maybe talking about hot peppers, they're about a 120-day crop. So if you're growing them outside and you only get 120 days, they're just starting to produce, and you're going to get frost, and they're not going to be. So it's not going to be worth the effort to grow them outside. Something to note is the red line. It gets pretty warm in the high tunnel, even in the wintertime. Usually you're not caring about your high tunnel in the winter because you're not growing anything out there, but it's getting up to 90, almost up to 100 a lot of times in the winter. So zooming in just to one day, this is February 7th. The blue line is the temperature in the high tunnel. The gray line is the outdoor air temperature. This actually was a really nice day for us. It got up to 37 above freezing on February 7th. But you kind of see in the high tunnel, actually in the nighttime here, the blue line, the high tunnel temperatures actually were below the outside air temperatures. And that's because the ground is cold and acts a little bit like an ice box in there. And so it'll get colder than outside. But it heats up fast, really fast in the high tunnel. And you guys probably noticed this. How many people here have a high tunnel or a greenhouse? Yeah, it's pretty nice to work out there in the winter. When it's sunny out, it gets warm fast. And this is actually pretty stressful on plants if you had plants growing, and then that's a pretty substantial shock. And then unfortunately it cools off equally rapidly when the sun starts to go down, and so that's kind of bad. It's really due to the low insulation level. This test greenhouse has the inflated polyethylene film on it, so that's really one of the better methods that you can cost effectively make a covering for a large surface area, and it's still not that great and kind of reduces our growing season.
Is that your average 20 degrees above the outside temperature? Is that kind of your year-round average for your high on a sunny day?
It will depend throughout the year. So this is in February, so our day lengths are starting to get longer. Like really the lowest temperatures above outside will be when our day length and our sunlight is the shortest in December. So it'll not get quite this warm around the December and January. A lot of times in January, it's also a lot of cloudy days, so it's cool. And by the time February comes around, the day length is it feels good. It's getting nice. And I'll talk a little bit more about the sunlight and day length here. Let's see, I had a couple bullets. So two big areas for improvement in the high tunnel exudes, like what can we do to reduce the amount of heat loss, and what could we do to reduce this temperature rise, because we have a ton of energy coming into our high tunnel that we just can't use, and it gets lost. And you can kind of see just overall, and this maybe answers the question a little bit, around the winter solstice, which would be right about here. You can kind of see this general trend where the highs do dip down, and that's just really due to the less sunlight. So what might a better tunnel look like? What if we maybe set some goals for the system to stay above freezing for as long as we have enough daylight that we could actually grow something? Because we're far enough north that in the wintertime, we don't have enough sunlight for a lot of types of produce to grow, even if you kept them warm enough. When is that? There's kind of a general rule of thumb. It's kind of is pioneered by Elliot Coleman, if anyone's read any of his books, like The Four Seasons or Gardener. He has kind of set the guideline. If you have less than 10 hours of daylight, we don't have enough sunlight for fruit-producing plants to produce like tomatoes or peppers or anything like that. You'll see people, you can still grow some vegetables like lettuces and other things that can handle lower day length, where you're harvesting the leaves instead of the fruit. But anyway, this time period where we don't have enough sunlight, he calls the Persephone period. And if you're into Greek mythology, Persephone was abducted by Hades and taken to the underground for a period of time each year, and that causes winter. And so that's why he comes up with that name. But anyway, we have more than 10 hours of daylight from February 4th, so we just passed that this last week, and up until November 6th. And so if you have been growing in a high tunnel or a greenhouse, you'll notice that by the time November's coming around, your crops aren't producing nearly as fast, even if you're keeping warm enough. So if we kind of looked at that, we have maybe 276 days of possible growing if we could keep our growing system warm enough, which is 114 days more than we have growing outside. So I'm going to step back and talk a little bit about the Chinese solar greenhouse. This here is a greenhouse. Has anybody here ever seen these, seen pictures of these? You can look it up on YouTube and find more pictures. But these are pictures of kind of what the structure looks like. China has the largest greenhouse-based vegetable production in the world. By 2010, they had already 1.9 million acres of production, food production in solar greenhouses, this Chinese solar greenhouse style. And that's a lot of acres. I think it's kind of hard to fathom what maybe that means. So I just put together this little Google Earth video here of Shenyang. Shenyang is in northern China, so they use these solar greenhouses quite a bit. But this whole region is covered with this greenhouse type system, and it's kind of crazy. I haven't been there to see any of these, but I've seen a couple of these in production. But anyway, the cool thing about that is there's all kinds of research and publications that have been done on these solar greenhouses, and I'm going to kind of take some of that research and information and apply that into our location, our climate, and built one here to see what it does. So looking a little bit at the frame geometry. What could we do to reduce the heat loss but yet make sure we get as much sunlight as we can? In a traditional high tunnel, in the summertime, summer solstice, our sun is at a 70-degree angle above the horizon, and of course easily shines on the whole structure. In the winter time, at noon, our sun is at a 22-degree angle, and you can kind of see you're not getting sunlight directly through many surfaces of that high tunnel, and so they're not really, it's not advantageous to have a clear film over those surfaces. So what could we do to maybe balance that? So what I did with this research project, the structure is shaped more like this, and the surfaces that are north-facing that aren't getting direct sunlight have an opaque insulated surface. Then we can insulate it and reduce that heat loss through those areas much better. But the dimensions are set up so that in the wintertime, we still have full sunlight to the growing bed and to the north wall. And then in the summertime, we don't have any shading happening in our growing area. Some structures I've seen will optimize it just for winter growing, like the Deep Winter Greenhouse from the University of Minnesota. They're focused on winter growing only, and then you wouldn't get full sunlight in the summertime. But the structure I set up so that we have year-round growing conditions. The entire area is illuminated. And then one of the big things that we saw is the temperature goes up fast and then it falls fast. What could we do to store that heat in a passive way that doesn't require any other energy inputs? In the Chinese solar greenhouse, they have a variety of different heat storage mechanisms. They'll do compacted earth, where this north wall is packed earth, or blocks that are concreted and assembled permanently. But what I used was to stay with the high tunnel objective of a temporary structure, these concrete blocks that are portable. And I'll show some more pictures of these, but they're 6-foot concrete blocks, 6 by 2 by 2. You can get these, they're used for retaining walls sometimes. A lot of the concrete places will have these available. They make them out of surplus concrete they have available. Maybe talking about this graph a little bit. So one of the reasons high tunnels get hot so fast and cool off so fast is because air is full of air and they can't store much heat. Air heats up very fast and then it cools off very fast because it doesn't hold heat a lot. But if you look at, say, concrete, it's much better. There's other things you could use to store that heat energy, but concrete is pretty simple and it's pretty reliable. The structure here is set up so that in the winter time, we have full exposure of those blocks to the direct sunlight so that they'll heat up as much as possible. And then in the summertime, actually, it will be shaded so that the blocks don't get direct heat, and they'll actually provide a bit of a cooling effect and reduce the severe high temperatures. So so here's what it looks like put together. You kind of see the blocks. They're about 4,000 pounds apiece, so they're big, they're heavy. Not maybe every tractor can lift them. I placed them with the tractor there in the picture, and it's kind of on the edge of what it can lift, but it did it fine. Any questions so far?
Does that do okay with snow load?
Mm-hmm. Yeah, I did design this so it could handle North Dakota snow loads, so the 50 PSF. Mm-hmm.
Was there a kit, or did you just do this?
This is my design. I did have the pipe all bent and formed at a local greenhouse or high tunnel manufacturer. So I didn't make the pipe myself, but I gave them the drawings.
Black tubing, you said? Is that, so that releases air from the?
Oh, yeah, the black tubes. So the black tubes are another part of this study that I'm collecting data on this winter, and I'll talk about next year. But the tubes are part of an in-ground heat storage system. So if you've seen some of those systems that take the hot air that you get during the daytime, store that in the ground, and then pull that up to heat. So it's a way to get even more heat storage capacity than just the blocks can provide. So in the future, I'll have data comparing how just the concrete blocks worked with the tubes. The tubes aren't a fully passive system because you have to have fans to blow the air through those tubes.
Since you're optimizing for sun angle,
Mm-hmm.
your width relative to your height, is there a ratio there?
Yes. There is optimal ratios to the height of the structure and then the depth. The length this way could be anything. That wouldn't be a big factor in it. For this study, I wanted to make sure that it's big enough. This is 60 foot long. I wanted to make sure it's big enough to get a factor of scale to get good quality data. If you make it shorter, you have more surface area per volume, and the performance is not quite as good, but I wanted it to be within a realistic range for most high tunnels. So how to go about making an insulated wall roof. This actually was maybe a little bit more interesting and challenging and innovative, I guess, because I haven't really seen anybody doing this much. To be a high tunnel, it needs to be a temporary surface. It'd be easy to just put up plywood and insulate that, but to be temporary, we need to be able to put it up and take it down and stuff. So what this consists of is basically 2 layers of tarp material. The outer layer is a vinyl tarp. I'll maybe go to the next slide. The outer layer is a vinyl UV-resistant external tarp, like you'll see with hoop buildings that are pretty popular nowadays. And then the inside is a polyethylene tarp that may be typical to what you'd go to the store and buy, because the cost is much less. But that's not UV resistant and it's going to break down fairly quick if you were to put that on the outside. And then in between those 2 layers is foam board. I ended up using 1-inch foam board, and it would be better if it was a couple inches. It would be worth it. But I had originally wanted to use mineral wool batting, and what I ran into was it wasn't rigid enough. Mineral wool, if you've ever worked with it, it is more rigid than fiberglass, and it's more mildew resistant. If you've done aquaponics, mineral wool is what they usually grow as the growing medium in aquaponics for your plants. But I couldn't get it to not sag, and you can see that in the image here too. Even with just the 6-foot spacing, it would sag. So you'd have to, in order to make this work, you'd have to put the little things like you do in quilting to keep the batting in the middle and not sag. So I ended up going to foam board, which worked really nice because you can just slide that in there between the 2 layers of tarp. And then the film area is pretty standard, high tunnel, inflated double polyethylene film, like you've probably seen and used on high tunnels. And then for the roll-up vent, I did a good bit of research on this. I was a little maybe disappointed with the amount of information and good parts and materials out there for roll-up vents. So put quite a bit of time into this. I did, for a couple months, I left the vent uninflated to kind of gather some data and see how much heat loss would have through that. A single uninflated layer of polyethylene has an R value of 0.85. 0.85 is like the resistance to heat flowing through it. What people run into a lot with uninflated vents is that they flap in the wind a lot. You hear a lot of people having issues with, these ropes that hold it down will break in the wind, and then everything will fall to pieces because the wind gets in there and rips stuff apart. And there's also, when it's windy, because this rolls up here, the cold air will blow in through the edge when we have a wind from the east or the west. But I did an inflated vent system, and here's kind of a picture of it, a little bit partially rolled up. And so when you are able to inflate, your R value goes up to 1.25, which if you were to heat, say, trying to heat this with propane to maybe maintain 45 degrees for the weather we had this year, and if your propane cost is $1.65 a gallon, which is about normal, you'd save about $140 a year in heating costs. So maybe that's a lot, maybe not really. But there's also other advantages. So how these works is that you have, of course, for your main surface here, you have an inflation fan, and then the vent has a separate inflation fan. So you can, in order to roll up, you turn that fan off, and then the air in the vent will flow out. there's actually slits in this piece right here that when you start to roll it up, it uncovers that opening, and then the air will go out, and you can roll it up successfully. And another really cool thing that I noticed is there's no issues with things flopping around in the wind. It's really nice and rigid and tight on that vent. You can feel free to leave it partially rolled up on a windy day and not worry about the structure being damaged. And it's really nice. And then along the bottom is what's called a roll lock channel. It's an aluminum extrusion that when this is unrolling, gets to the bottom of the plastic, and then it rolls up and under this loop and is tight and sealed. So here's some fun engineering thermal pictures. I don't know if you guys have seen thermal pictures before, but generally the colors will tell you the temperature of surfaces. Generally, not exactly. It's kind of hard to get good pictures of the film because it's also kind of shiny and reflective. But you can see in the non-inflated vent here on this side, it's redder, it's warmer, more heat is coming out of the structure through that surface, whereas when it's inflated, we have a uniform color and temperature to that. And I screwed up when I saved these pictures, and I got one in Celsius and one Fahrenheit. But it's kind of neat here because I talked about your radiant heat loss to the sky. And here you can see the sky is very nice and cold and blue. And the sky temperature on these nights when I took it was minus 40 Fahrenheit. So that's a lot below what the air temperature is. And so that's why you can get frost damage before the air temperature is freezing on your plants. Now I'll talk a little bit about the concrete blocks and how that worked out. This was just a fun picture I took before I had the covers on, actually after dark, and the blocks are warm and radiating heat like they're supposed to. So for this part of the study, I drilled holes in the concrete block, 1 inch deep and 8 inch deep. I wanted to do 12 inches, but my drill and my arms did not want to do 12 inches of drilling to get the probes in there. And this is maybe a highlight of something that I would not do in the future. I had designed this so that the pipes mounted to the top of the blocks. And the concrete blocks are made from basically waste concrete. When the concrete cement company goes out and they pour a driveway or they pour a foundation, they have some extra material left over in their truck at the end of the day. And they have some molds that they pour that extra material into. And so instead of wasting that cement, that concrete, they're able to form it into molds and make these blocks and sell those to people. So the block costs are really cheap, and it's really a waste material that would have to be disposed of anyway. What that does mean is that every block tends to be a little bit different because they have particular types of aggregate and materials that they're doing for a driveway versus a highway versus your foundation. And we have beautiful red Sioux quartzite aggregate in our area, and it's really hard and impossible to drill through. So it was very difficult to drill the holes and get the pipes attached to the top of the blocks. So I don't recommend that. And it also made it very hard to get the probes into the blocks to record their temperatures. But then I had set up one block dyed black, whereas the rest are natural colored for part of the study to see what the difference would be in heat storage between the black and the natural block. So here's a little summary of that. This graph is the temperature difference between the white block to the black block. And you can even see in the thermal image, the block that's painted black at the end of the day is measurably warmer than the natural ones. I was a little bit concerned about having to paint the blocks and if that was really worth the effort to do that. Of course, it costs money to put that dye, that concrete dye on. I was also just concerned about having that near the growing area, and so I wanted to try it without that first and see what the effect would be. So this here's our temperature difference between the temperature sensors at 1 inch and 8 inch of depth. And we'll see, you kind of see on the spikes here, this is just January 4th through February 15th. And you can see basically which days are sunny days because the blocks heat up on those sunny days. But we actually see on the painted block almost 75,000 BTU of heat energy is absorbed in that outer 8-inch layers more than the normal unpainted block, which is substantial. For reference, a gallon of propane is 92,000 BTU. So every day that it's sunny, you can get a free gallon of propane if you paint your blocks black. So I went ahead and dyed them all black in late February so that I could do the rest of the study with them black. And that's kind of what they look like. And the tubes, tubes are here, now, and those aren't part of this test, but will be next year. So overall, looking at the block temperatures for this time period and how much they heated up and cooled, we'll see really a temperature increase of up to 31 degrees just in the outer 1 inch of that block. So they're actually heating up quite a bit. Of course, once you get farther into the block, it takes time for that heat to conduct through, and it's not heated up as much. But still 12 degrees, which is pretty good. So that ends up being approximately 225,000 BTU absorbed every day on a sunny day for that entire block wall, which is a lot. So how did it do? So this is our same weather graph you've seen before with the high tunnel temperatures overlaid on it. Here the black line is the same 4 foot above the ground air temperature, and the red line is the daily high. So I was surprised by this. Actual last frost date, or last time it was 32 degrees, was February 28th, which was surprising to me. We had some pretty cold temperatures here in March, late March, that got well below freezing. But with the blocks, it was able to stay pretty good. And that's plus maybe more than 85 days of additional growing season. So a total of 247 frost-free growing days, which is huge. Some of the kind of key neat things you can see on the graph, this is our really cold spell that we had in February, whereas the regular high tunnel stayed 10 degrees above the outside air temperature. Here we're staying, this is actually the lowest temperature I recorded in there. I thought I had this labeled on here, but it was 15 degrees Fahrenheit. So, yeah, that's the label. So 15 Fahrenheit. Of course, that's still freezing temperatures, but that is a lot more than negative 20. So that really opens up the doors to growing a lot of different types of things in a structure like this. I had a couple plants that I thought might survive that I put out in the high tunnel over the winter. So I had a fig tree out there, and it was just in a pot, but it survived the winter just fine, which is exciting. So this climate ends up being something like a zone 7 or zone 8, if you're familiar with the USDA zones, which are just based on the low temperature of the year. So they don't tell you a lot, but if you wanted to overwinter fruit or vegetable plants, that's a good reference point there. But having 247 growing days is pretty awesome, because you could, by what you're growing, you could grow a lot of things. Any kinds of crops that maybe would grow around the Mediterranean type climate, they would do well in this situation. A lot of citrus actually is hardy down to 15 Fahrenheit, so many types of citrus could be overwintered in this. Of course, figs, pomegranates, all kinds of things for us that are exotic.
Are you a little concerned that you probably have a lot of days that are over 100 degrees?
Yeah, so depending on what you're growing, it's getting just above 100. The actual regular high tunnel was getting more than this, which I don't really have that overlaid on here, but this is actually cooler than the fan ventilated high tunnel, which I thought was interesting. You can kind of see in the data here where we're kind of getting some high temperatures each day, and then as it gets into May, that actually goes down, and that's because then the blocks are being shaded by the angle of that roof, and then not until, so it's set up so that the 3 months around the summer solstice, the blocks don't get direct heat. It was February 18th or 19th here where I had the blocks were white and then I made them black at that point. And so I think that also causes that high temperature to go down a little bit because they're absorbing more of the heat and stabilizing the temperature further from the white blocks. There's an overall comparison. Outdoor, I had 162 growing days above freezing. High tunnel had 190, and the extended season high tunnel had 276. And if anyone has other ideas of things to look at with the data, other metrics, I think that would be great. I could do that with the data. So maybe, Harleen, maybe you have some other ideas of things I could look at with that. Let me know.
You mentioned earlier about the amount of sun that comes in still is a pretty large limiting factor. If you're able to keep the greenhouse warm, you can grow the leafy vegetables, lettuces and stuff like that, early season, late season. Have you done anything in terms of trying to adapt or find vegetables or fruiting vegetables that fit this mold?
Yeah, so what I had shared was just the length of day, our daylight length. I had not originally recorded what the amount of day sunlight was. So starting this fall, I added some sensors to measure what our total amount of sunlight is that we get each year. So then I can calculate the DLI, the daylight integral. So then we can look at different crops that have published DLI requirements to see which ones would survive or would be productive in those environments. I hadn't really come across that info anywhere. I don't know, Harleen, if you've seen high tunnel measurements of sunlight through the winter time. Christine didn't have anything on that.
No, they were measuring, her husband was measuring temperature
Yeah, he measured ground temperature.
and how that varied in the high tunnel.
Yeah, so I'll have data starting in November. I added the sensor, so I'll have that through this winter.
At least you'll know what you might do. You still don't have everything.
Right. I've seen one study from the University of Minnesota where in the deep winter greenhouse, they did a study measuring the sunlight, and they trialed different varieties of lettuces in that and measured the amount of productivity of different cultivars for lettuces. So that does exist, but that's using a double wall polycarbonate glazing, which has a little different light transmittance than the films do.
Yeah, what I've heard is that it doesn't make a difference if it's warm enough. You just don't get enough sun.
Right.
Could you supplement that with having lights on a timer?
Yeah, you definitely could. You can add lights, and I do that in my greenhouse a little bit for things that I care about and want to have more productivity. Of course, if you add growing lights, that adds a lot of cost, but those also put out a lot of energy or that they're using electricity, and all that ends up being converted to heat in the end too. So that increases your temperatures too. So grow lights, of course, they're adding light, but they're also adding heat, and so they're kind of like little space heaters. So, but they add a lot of cost. So that's most of all the data stuff. I figure it's important to share some plant pictures because we want to see green stuff here. And this was just a little bit overwhelming for me because I didn't expect the level of productivity. So I planted peppers, hot peppers. Partially, I had somebody that could buy some of them, and because they're excellent temperature sensors because they're very frost sensitive, so I can see when parts of the high tunnel freeze. So I got them all in the ground by April. I didn't have them started soon enough because I didn't expect it to be frost-free by the end of February. If I had been on the ball, I would have had them ready to plant in March. So April 21st, I got them all in the ground. By June 2nd, they're looking like this, nice peppers. These happen to be scorpion peppers, which I don't know if you're familiar with those. They're pretty hot. They're not Carolina Reaper hot, but they're hotter than ghost peppers. They have a long growing season, typically a 120-day plant. So difficult to grow successfully outdoors. By June, they're looking like this, pretty big for June. By July, wife for scale here. By July 20th, they were more than knee high. So they're on the verge of competing with our corn for height. August 17th, this is one of the fellows that helped me with the CAD work and all the design stuff we did. The peppers are approaching 6 foot high. I did not prepare for the level of growth because peppers aren't known to get this big, not like tomatoes. So my trellises were only about 6 foot tall. But by September 23rd, it was crazy. And December 5th, this actually is the first bit of frost damage that I started to see this year. You can see up on the top here, we got a little bit of frost damage. And this is the trellising method I ended up resorting to, and I call the waterfall method now, where it just goes up and falls all over the place. And this is really how I felt. So if anybody wants hot peppers, I got them. If anybody's interested in a tour, I'm located by Brookings. Reach out, send me an email, and you can come tour and check out the high tunnel. It's pretty cool, and pretty pictures of Carolina Reaper peppers. And of course, special thanks to the South Dakota Specialty Crop Block Grant Program for making this possible. It's a really exciting study, and being able to grow produce locally for that length of time gives us a lot of options.